Imagine trying to build a city where the post office refuses to issue any new street addresses. You can't get mail, you can't get deliveries, and eventually the city stops growing. That is exactly what has happened to the internet. We have officially run out of original addresses. Every single device connected to the internet, your phone, your laptop, even your smart thermostat, requires an IP address to send and receive data. It functions exactly like a digital mailing address. Without it, the network wouldn't know where to route your information. When the internet was designed in 1981, engineers built a system called IPv4. It used a short sequence of data bits to create addresses. Think of it like a telephone number with only a few digits. There are only so many combinations you can make before you run out of unique numbers. In this case, the limit was 4.3 billion. In the early 80s, a few billion addresses seemed like a massive supply for a small network of research computers. But planners didn't anticipate a world where 15 billion devices, from smartphones to smartwatches, would all be fighting for a spot on the network at once. The supply didn't dry up all at once. Between 2011 and 2020, the regional registries that hand out these addresses slowly emptied their reserves until the global pool was completely bone dry. Without a way to give new devices an address, the internet should have hit a hard wall. The sheer volume of new hardware would have overwhelmed the system, freezing the expansion of the digital world entirely. So, if the central supply ran out years ago, why hasn't the internet collapsed? The answer is a clever, temporary workaround. Engineers kept the system breathing using a technology called Network Address Translation, or NAT. NAT treats your home internet like an apartment building. Instead of giving every single device its own public address, your provider gives one single address to your home router. Your router then acts like a lobby receptionist, sorting incoming mail and routing it to the private internal addresses of your phone, TV, and laptop. Internet providers eventually had to take this trick a step further. They use a massive version of this system to funnel the internet traffic of entire neighborhoods through just one single public address. This workaround keeps us online, but it comes with heavy performance costs. Devices can no longer speak directly to one another. Every piece of data has to be stopped, unpacked, translated, and repackaged by routers along the way, creating processing bottlenecks and increasing delay. The original IPv4 system makes this even harder because the digital envelopes carrying your data vary in size. Routers have to spend extra time figuring out how big each envelope is before they can process it, slowing things down further during heavy traffic. This patch job successfully bought us time, but it resulted in an overly complex, inefficient system. To handle the future, we needed a permanent replacement. The permanent solution is a redesign known as IPv6. It uses a sequence of data 4 times longer than the original system to create addresses. Because these new address strings are so much longer, the number of possible combinations explodes. Instead of a few billion, we now have a pool of 340 undillion addresses, written as long strings of letters and numbers. To put that scale into perspective, you could assign hundreds of quintillions of addresses to every single square meter of the Earth's surface. With that kind of vast supply, the complicated lobby receptionist workaround of NAT is completely unnecessary. Every single sensor, phone, and server on the planet can have its own direct, unique public address. Ditching that middleman restores direct, end-to-end communication across the internet. Without the constant delay of translating addresses at every stop, data flows at more stable speeds, even when networks are under massive strain. Engineers also cleaned up the data envelopes. IPv6 uses simple, uniform envelopes that are always the same size, allowing routers to process traffic much faster. It also has built-in security features, making encryption a native part of the network. This redesign makes the internet faster, safer, and ready to support every device we will build for the foreseeable future. The challenge we face now is that the old system and the new system speak different languages. An IPv4 device cannot directly communicate with an IPv6 device. This technical diagram illustrates the main transition strategy, called dual stack. As you can see in the center block, devices and routers are configured to run both address systems side by side. When a dual stack computer wants to load a website, it checks the internet's directory. If the destination supports the new system, it prefers the faster IPv6 connection. If the destination is outdated, it seamlessly falls back to the older language. In situations where a modern IPv6 message has to travel across an older stretch of the internet, networks use a trick called tunneling. The modern packet is simply wrapped up inside an old IPv4 envelope, sent through the pipe, and unpacked at the other side. This massive migration is happening right now. Your devices are constantly navigating these two worlds, traveling through both old and new pipes behind the scenes. This shift is a highly orchestrated evolution of a network that will provide more than enough room for every device we build for generations. Rebuilding the digital post office while the mail is still being delivered ensures the internet never runs out of space again.